Here then is an algorithm that will take you through the complicated process of finding where a function is increasing or decreasing. Let f be continuous on the closed interval from a to b. To find open intervals on which f is increasing or decreasing, first of all, you need to find your critical numbers. So, you may have to turn your head sideways for this. Just saying. Okay, locate the critical numbers of f in your open interval from a to b. How do we do that? We find the first derivative and set it equal to 0, or find where it does not exist. Use those to determine your test intervals. So those test intervals, you originally take the domain of that function or whatever interval that they give you to begin with, and you're going to use your critical numbers to break that up into some test intervals. Okay, and all we need to know is the sign of the first derivative in those test intervals. Determine the sign of f prime of x on each one of those intervals using your test value. You just plug it in. Is it positive? Is it negative? Because if the first derivative on your test value is greater than 0, everything in that interval, the derivative is going to be greater than 0, and we know that it must be increasing on that interval. If we plug it in and we get a 0 value, then we know that it's supposed to be constant on that interval. This one is probably not going to happen, right? Not unless you have yourself a horizontal line within your function. And then finally, if you stick your test value into your first derivative and it produces a negative number, then we know that it must be decreasing on that interval. All right, let's try this one more time on example 5. Find the open intervals on which f of x equaling x cubed is increasing or decreasing. This should be easy. Look at this. It's a cubic polynomial once again. All right. Where do I start? I start by taking the derivative. So f prime of x is equal to, I'm pretty sure, 3x squared. Okay. Now we need to find our critical numbers, setting that thing equal to 0. And I'm going to say that our critical number is only one of them, and its x is equal to 0, critical number. What's the domain of this function? Since it is cubic polynomial, it's got to be all real numbers, so that's what we're going to use to set up our test intervals. So once again, this is testing for increasing or decreasing. Test for increasing or decreasing. And I just set myself up a little table of intervals to test with a sign chart. We're going from negative infinity to 0. There's our first one, and then our second one from 0 to infinity. Just two things to test. And speaking of tests, we need to find some x values in each of these. Pick something super easy like -1 and +1. Where do I put those values? I put them into the first derivative, because we want to see, is the first derivative positive or is it negative in each one of these intervals? Remember that the first derivative is equal to 3x squared. So when I stick in -1 here, that negative gets canceled out by the squaring, and it's going to be positive here, indicating that f of x must be increasing on that interval. Do you know what to expect now? Shouldn't it just alternate? Here, let's see. If I put in a +1 for my x squared, it's still positive. And our function is still increasing. Whoops, that was supposed to be blue. Let's keep it consistent. Increasing. Did that subvert what you expected, that they were going to alternate? So don't get used to that, these things are always going to alternate. You can see that it stayed positive. It's increasing over this interval. It's increasing over the other interval. What about at 0? Well, it's still increasing through 0. We can take a look at the graph here. All right, there it goes. And take a look also at the first derivative in green. You only have one critical value. It happens right there at the origin. But what about the function? Sir, the first derivative is equal to 0 there. It's not positive, it's not negative. Doesn't matter, the original function is increasing for its entire domain. It's increasing everywhere. So if I were going to write this up, I would say that My function f of x is increasing everywhere because the first derivative, f prime of x, is greater than 0 on, specifically, it's not positive for the whole entire domain. It's only positive from negative infinity to 0 union 0 to infinity. But we can use the definition of increasing to show that it's actually increasing through 0. But we can also see that in the graph. It's increasing everywhere, and there is a name for that. It is called strictly monotonic. We say our function is strictly monotonic on an interval if it is either increasing or decreasing on the entire interval. Find two functions that are strictly monotonic over some interval, one increasing and one decreasing. So this is a thought experiment for you, but I can give you a hint. You've seen one every single time you've turned on one of my videos, just saying. All right, so in the next lesson, we're going to see how we can use the same exact kind of test that we were doing for increasing or decreasing, take it a step further in order to be able to conclude whether or not we have a relative minimum or relative maximum.